I mean, it's amazing, no? All these soft.
Hi students, good morning. Welcome to the Go Vidya. As part of previous year question online session, today also we are going to solve some questions related to the transformers. Okay, in last sessions we discussed many previous year questions related to transformers. If you observe those questions, most of the questions are repeated from the efficiency of the transformer and voltage regulation of the transformer and auto transformer and voltage regulation and this one what I can say EMF calculation of the transformer. So if you observe near about the 40 questions, mostly 3-4 topics are repeated. So what my sincere suggestion is, if you are focused on these 4 basic concepts, you can solve at least 60 to 70% questions. Okay, so hope this session will helpful to understand the basics of how to solve the different questions. Okay, so if you have any doubt, you can contact our support team as shown in the screen. Okay, so we are providing offline classes, online classes as well as test series also. Okay, if you have any support, you can contact our helpline number. Okay, let's start the session. The question is about, in an auto transformer, power is transferred through. Okay, if you observe the concept here, the auto transformer power transfer. Okay, if you see the basic diagram of a auto transformer, the same winding we are going to use for both primary as well as secondary. Okay, in auto transformer we are using same winding for both primary and secondary. That means the power is transferred through electrical, that means conduction process. First thing what you need to understand, conduction process. Second thing is, it is on the core, the winding is placed on the core, so some amount of power is going to be transferred by the process of induction also. This is core. As like we studied in two winding transformer, same flux steering, that means mutual coupling. So power is transferred from primary to secondary. Clear? So in auto transformer, not only through induction process, through conduction process also power is going to be transferred. How conduction process means, the same winding we are using for both primary and secondary. Because of that, electrical conduction is going to happen. By that, power is going to be transferred. Clear? So our option is both conduction and induction process. Option C. Okay, let's move on to the next question. The question is given is about auto transformer. Just look at here, auto transformer they given. The turns ratio of auto transformer is NAC by NBC equal to 1.5. Okay, here they shown one figure. Let's take figure as figure 1. They given one figure of auto transformer and they given the turns ratio. Next, what are the other details given? Let's see. Considering equal loads and for the same heating in the windings, the ratio of equivalent resistance of auto transformer to two winding transformer. Okay, they are asking ratio of equivalent resistance. The question is about calculation of equivalent resistance. Okay, whenever this type of question will come, we have to break down the question in part by part. First, let's see the concept. On which concept the question is came. Concept is about auto transformer. Okay, so in auto transformer, percentage tapping is K. Okay, or you can say K equal to, what is K? LV turns by HV turns. That means K is equal to NBC by NAC. We know that K equal to LV by HV. From that we can calculate K as 1 by 1.5. Okay. So whenever you are getting any problems related to auto transformer, the first step is you need to calculate immediately K. Why means most of the questions we can solve if you have a value of K. We already discussed in the previous year question in the last sessions the power transfer of auto transformer compared to two-winding transformer, voltage regulation, copper saving. So many factors we can calculate from the K value. So for the first step, when you see the question about auto transformer, is to calculate transformation ratio K. Okay. Next, what they are telling? They are telling same heating. Okay, same heating. What is same heating? That means if you use a auto transformer and two-winding transformer for same load means the load is same. If load is same, the current drawn from the transformer is going to be same in both cases. So they are telling about heating. Heating is nothing but how heat energy will generate. It is from the losses. So most of the losses are in transformer is copper losses. Copper losses are depends on the load current. As they are telling the same load is connected, so current is going to be constant. Okay, that means the copper loss in both auto transformer and two-winding transformer is same. They are telling. What they mean to say here is same heating means from the term same heating we can write it as R auto. That means resistance of auto transformer I square R two-winding. Okay. So what is the copper losses? We know I square R. For two-winding transformer, copper losses are I square R auto. For for auto transformer, the copper losses is I square R, and for two-winding is I square R TW. So this is the given data. They are already given. Okay. So in order to find the ratio of R auto to R TW, we need a relation between the I auto to I two-winding. Okay. We already know that the rating of a transformer is how we can give KVA, V into I. Okay. So from here the rating of S auto is directly proportional to the I auto and STW is directly proportional to the ITW. Okay. So if you know the rating of auto transformer and rating of two-winding transformer, then you can find the ratio of R auto to RTW. Is it clear? Okay. So let's move on to the solution. We need to calculate S auto. How we can calculate? We already know S auto is equal to 1 by 1 minus K into S two-winding transformer. That is, power rating of auto transformer is given as 1 by 1 minus K into power rating of two-winding transformer. If you have a ratio of S auto to STW, how much it will come? 1 by, what is K? 1 by 1.5. That 1.5 you can write it as 3 by 2. From this what will come? 1 minus 2 by 3. 3 by 1. So S auto by STW is equal to 3. Okay. Let's take this is equation 1. That means S auto is directly proportional to I auto current. Let's take it as equation 1 and this as equation 2. From 1 and 2, what you can write as I auto divided by I 2 winding is equal to 3. Okay. So what do you know? From the given data, I square auto equal to I square auto into R auto equal to I square TW 2 winding transformer copper loss is going to be same. Okay. So we need a ratio of R auto to R 2 winding. So it will be ITW divided by I auto whole square. Here we already calculated I auto by ITW. How it will be? It will be 1 by 3 square. Then it will come 1 by 9. Okay, our answer is R auto divided by R 2 winding equal to 1 by 9. Option is D. Okay. Hope it is clear. Okay, I would like to just give the synopsis of this answer. See here what they are asking. They are asking about the ratio of equivalent resistance. That means transformer auto transformer equivalent resistance to two winding transformer. They are asking. What are the given data we are having? They are telling same heating. From same heating, what we extracted for same load, same heating means the losses of copper losses in auto transformer, copper losses in two winding transformer is going to be same. Okay. From that, you can get the ratio of auto transformer resistance of auto transformer to resistance of two winding transformer. Okay. So my sincere suggestion is, whenever this type of problems will come, it may look like lengthy, but if you understand the basics, the solution is very, very simple. So whenever any question related to auto transformer came, first and foremost thing we need to do is calculation of K. Okay, calculation of K you need to find out. If you have the value of K, you can calculate any parameter given in required parameter from the K. Okay, is it clear? Hope my explanation is clear for all. We'll move on to the next question. Okay, the next question is about the core of two winding transformer is subjected to magnetic flux variation shown below. Okay, they given connection of the two winding transformer and the variation of that means flux waveform also they given. This is the flux. What they are asking, the waveform of secondary induced EMF. What they need to asking to calculate secondary induced EMF. Secondary induced EMF. So first we will note down the concept. From which concept it came? The concept is about calculation of secondary induced EMF. What are the different formulas we remember related to induced EMF in a transformer? E2 is equal to N2 into d pi by dt. Okay, N2 into d pi by dt. So no need to calculate all time intervals of this derivation. Okay, d pi is but just observe the given options once. So since it is a ramp, if you differentiate a ramp, we are going to get a square waveform. Is it clear? So in positive side only that square waveform need to be there. Is it clear? If you observe like that, how many options you are matching? Two options. One is A and C. Okay, A and C. If you differentiate any constant, what you will get? 0. So in both A and C it is matching. And what is the main difference between A and C options? the interval between 0.12 to 0.12 to 0.1 sorry 0.1 to 0.12. In this duration the voltage induced is different. Okay, we need to find out that. How we can find out? It is a declining ramp. Okay, declining ramp. So induced EMF V2 is equal to N2 into pi 2 minus pi 1 divided by T2 minus T1. Okay, so N2 is 500. What is pi 2? Before that 0.009, sorry, pi 2 is 0, pi 2 is 0, pi 1 is 0.009 divided by T2, 0.12 minus 0.1. How much it will come? 500 into minus 0.009 divided by 0.02. After calculation, how much it will come? It's near about minus 2 to 5 volt. The induced EMF is E2 is equal to minus 2 to 5 for the duration 0.1 less than T less than 0.12. Okay, see here, sometimes we need to just see the options which is suitable option we need to select. Why? Because if you want to calculate for each interval, it is a time taking process. Your time is going to kill. Most of the questions are designed such that by seeing the option itself we can identify the answer. Okay, so we have to use some tactics while solving these type of questions to save the time. Why? Because if you are consuming more time on this, you may be lagging in time. That will increase pressure on you. That may, if you are in pressure condition, okay, then we are not able to solve the question correctly. Okay, so these all are tactics they are going to play by the examiner. Okay, is it clear? So our option is C. Let's move on to the next question. The next question is about a 3.3 kV by 400 volt single phase transformer required 330 volts to allow full load current at pi SC. Pi SC is the angle, short circuit angle. Okay, 75 degrees. Its voltage regulation at full load 0.707, lagging is. Okay, it is a combination of 2-3 concepts. Okay, it is a combination of 2-3 concepts. You need to break down the question. We will go step by step. First, what they are telling, they are telling full load current at pi SC. Okay, what they are telling, if you apply 330 volts at primary side, it is going to drive rated current in the secondary side, and the angle between the voltage and current phasor is pi SC is going to be 75 degrees. Okay, and one more concept they are asking about voltage regulation. Okay, voltage regulation. First we will note down the formula related to voltage regulation. Okay, percentage voltage regulation is equal to percentage R cos pi plus percentage X sin pi. In order to calculate this regulation, we need percentage R, how much we need to calculate, percentage X we need to calculate. Okay, so what is the relation between the short circuit test and the voltage regulation is the percentage impedance is equal to the percentage voltage required. You might have studied this concept in the short circuit test of a transformer. The voltage required at primary side or the voltage required at primary side to drive rated current in secondary side. To drive rated current in secondary side. So into 100, okay, into 100, since it is a percentage. What is that? They given 330 divided by the voltage they given is 330. We need to calculate the ratio, that is 330 divided by 3.3k into 100. It will come around 10%. Okay, if you know the percentage Z, we can calculate percentage R and percentage X. You might have studied in networks how the cos pi SC is equal to percentage R divided by percentage Z. Okay, where pi SC already given as, pi SC is given as 75 degrees. Okay, from this cos pi SC, how much it will come? You need to take some approximate value, that means 0.258. Sin pi SC is about 0.96. I am taking approximate values. Okay, and sin pi SC is equal to percentage X divided by percentage Z. From these two formulas you can calculate percentage R. Percentage R, how much it will come? It will come around 2.58. From this you can calculate percentage X, how much it will come? It will come around 9.6%. Okay, so what they are asking? Voltage regulation. We already know the formula. Let's substitute the data into given formula. How much it will come? Percentage regulation is equal to percentage R cos pi plus percentage X sin pi. How much you got percentage R? It is around 2.58. Cos pi, they are telling given pi, they given as 0.707. This is the power factor, lagging power factors. That's why you taken positive here. Okay, cos pi is 0.707, and sin pi also is going to be 0.707. Why? Because it is pi is 45 degrees. Pi is 45 degrees. So 9.6 into 0.707. After solving this, we can get percentage regulation as 8.66% around. Is it clear? Let's see the options suitable for us. The suitable option is B. Okay, I am going to summarize the solution here. Actually, this type of questions will come little rare, but if you have strong basics of your subject, you can solve very easily. So how we solve this question is, we break down the question into two parts. Actually, it is a combination of short circuit test plus voltage regulation calculation. What is the common relation between these two concepts is percentage impedance. In short circuit test, you might have already studied percentage impedance is directly equal to the percentage voltage required to at primary or percentage voltage required of rated voltage applied on the primary side to drive rated current in the secondary side. From that we can calculate the percentage Z. If you have percentage impedance, then you can calculate percentage R and percentage X. After calculating percentage R and percentage X, we can easily calculate the percentage regulation. So if you break down the question into step by steps, the solution is very easily. Okay, let's move on to the next question. The next question is about, in a three-phase delta transformer, one phase burns up. The transformer will supply. I think in the last session we already discussed about this question. Okay, I think some new students are joined, so we'll explain the question again. Okay, so what they are telling, the given question is about delta transformer. They given delta delta transformer they given. What happened? One phase got burned out. That means one phase was faulty and it got removed from the system. Okay, one phase got burned out and it was removed from the system. Then how it will look like? It will look like open delta or VV type. Okay, this type of connection is called open delta connection or VV type connection. Let's see the different electrical parameters of the connection. This is the line voltage that equal to V1. This is, let's take this is the I1 is the phasor current. So IL is equal to, in delta system, line current is equal to root 3 into phase current. Okay. Here what is the different parameters? This is I1. Our line voltage VL is equal to V1. Okay. So what they are asking, the rating of the open delta. That means this type of connection is called VV or open delta connection. So if one phase got burned out, how much, at what rating the power, the transformer is going to be work, we need to calculate. For that, first we will calculate the rating of delta delta. Okay, rating of delta delta rating transformer we will find out. How we will find out? The three phase rating we can find out as root 3 VL into IL. Okay, from this figure 1, let's take it as 1 and let's take it as 2. From figure 1 you can write it as the line voltage is V1 and the line current is root 3 I1. It is going to be 3 V1 I1. Okay. In VV type rating, root 3 into VL into IL. This will be same. The formula is same, but the parameters we need to calculate from the diagram. Root 3 into V1 into I1. Okay, we need to calculate rating. If you see the option that are in percentage, so we are going to calculate in percentage. Let's take VV rating divided by delta delta rating. The ratio, if you find out here, is root 3 V1 I1 divided by 3 V1 I1 into 100. Since they are asking in percentage, how much it will come? 1 by root 3 into 100. It is around 57.7%. Okay, so what is the 57.7%? Therefore, the VV rating equal to 57.7% of delta delta rating. What it means is, even though one phase got burned out in the delta delta transformer, the remaining winding is going to transfer the power at the rating of 57.7% of the delta delta connection. Okay, so our option is about A. Is it clear? If you have any doubts, please chat over the comment box. I will explain wherever you got stuck. Okay, so this is about VV type of connection. Let's move on to the next question. The next question is about in an auto transformer, power is transferred through. Okay, I think this is also repeated question. The answer is both conduction and induction process. I already explained in today's session itself. I think this question got repeated. So in auto transformer, the power is going to be both transferred through both conduction and induction process. How means, if we see the winding connection, the same winding we are using for primary as well as secondary. So the two windings are connected electrically. So it is going to be conductive process, and as similar to two winding transformer, the flux is going to be shared. The primary flux is going to be shared by secondary winding. Okay, so it is going to be transfer some amount of power through induction process also. Okay, let's move on to the next question. The next question is about Buchholz relay is. Okay, this also important question. Many times this is repeated. Okay, so if you want to know about Buchholz relay, first we need to know where this relay is placed. Okay, if you see any transformer connection, this is our transformer core and this is transformer winding. This is kept inside the one tank and filled with oil. These are the winding provision. Okay, so whenever oil get heat, that oil will get expand. Okay, this expanded oil going to be the conservator tank. Let's take it as conservator tank. Okay, one pipe will be connected to the conservator tank. Whenever more heat generated in the transformer, that means more load is going to supply by transformer, oil will get heat up and oil will get expand, and expanded oil will go to the conservator tank. Okay, so in order to analyze whether the heat is generated only due to the high load or any fault, okay, any fault, that means if any fault occurs inside the transformer, the heat generation process will be very fast. Okay, and it will whenever oil will get heat up, it is disposed into the gases. Okay, disposed into the gases. We need to analyze the situation whether the heat is generated due to load current or any fault current. We are going to use the Buchholz relay. In general, this Buchholz relay is going to be placed in the channel of main tank to the conservator tank. Okay, so what this Buchholz relay will do, it is a gas operated relay. One float will be there like this. Okay, one float will be there like this. Here oil flow will be there. Okay, it is like making one switch, mechanical switch. Okay, it is like a mechanical switch. What will happen if sudden rise in temperature will leads to release of more gases? Okay, when more gases will come, oil quantity will get reduced and it will completely occupied by the gases. This is gases. Okay, all of a sudden these gases will lift the float like this. Okay, whenever this float will move up, then it will make the contact and it will send the trip signal. Okay, it will send the trip signal. This is the operating principle of Buchholz relay. So if you see the process, the operation of Buchholz relay is mainly depends on the gases. So you see what are the different options given. Voltage sensitive device, no. Current sensitive, no. Current, no way we are measuring here. Frequency sensitive, no. Gas actuated device, it is correct. So our option is D. How it is gas actuated device? In general, whenever load current is increases, transformer winding will get heat up, then the heat is transferred to oil will get expand. Okay, when the oil get expand, some amount of gases will release. These gases are going to trap that Buchholz relay. Okay, so if all of sudden if any fault occurs, then the gas volume will be more. So these gases is going to be lift the float upwards, then it will make the trip signal. So the main working principle of Buchholz relay is gas actuated device. Is it clear? The next question is about Scott connection. If the ratio of the main transformer is K, then the TJ transformer has a transformation ratio of. Okay, first of all we need to know how the Scott connection is connected. Okay, Scott connection is connected. What is the purpose of Scott connection is? Okay, we need to just discuss some synopsis related to the Scott connection. So in some of the industrial applications, we may require two-phase supply. Such as we may require two-phase supply. The applications are arc furnace, and welding. I'm talking about the industrial applications. In general, we are having a single phase supply and three-phase supply, but some applications require two-phase supply. in order to generate two-phase supply from the given three-phase supply, we are going to use SCOT connection. Okay, SCOT connection is mainly used for generation of two-phase supply from given three-phase supply. Okay, in general, three-phase and single-phase supply is available. From this, we are going to generate two-phase supply. Okay, so how the connection will be? We'll see. We need two transformers. The transformers will called as main transformer and TZ transformer. This is V2. It is going to be tapped at 0.866 V1. It is going to be 0.5 V1. It is going to be 0.5 V1. This is called main transformer. This is called TZ transformer. This is here we are going to apply supply a phase A, and this is phase B. This is phase C. Okay, this is a special type of connection for developing the two-phase supply. Why like this we need to connect is, for two-phase supply we need a phase difference of 90 degrees. Okay, we need a phase difference of 90 degrees. In order to get 90 degrees phase shift, you need to connect the two transformers, main transformer and TZ transformer, like this. Okay, from this we can calculate what they are asking: transformation ratio. First we will calculate the transformation ratio of main tank. K main tank is equal to N2 by N1 equal to V2 by V1. Okay, for TZ transformer, KT is equal to what is V2? V2 is V2 and V1 is 0.866 V1. You can write it as V2 divided by, this is root 3 by 2, you can write into V1. It will be 2 by root 3 into V2 into V1. You can write as 2 by root 3 into Km, where Km is the transformation ratio of main tank. Therefore, TZ transformer KT is equal to 2 by root 3 into what the given K main transformation ratio of main tank is given as K. Okay, the suitable option is A. So I am going to summarize the solution one more time. See, the given question is about SCOT connection. SCOT connection is you are using for conversion of three-phase supply to two-phase supply. For two-phase supply, we need a phase shift of 90 degrees. As in three-phase system, we are having a phase shift of 120 degrees. Okay, so in order to generate this phase shift of 90 degrees between the phases, what we are going to do? We are going to do the special type of connection. For that, two winding transformers we taken. One is called main transformer, another is called TZ transformer. As shown in figure, the connection will be there. So they are asking the transformation ratio of the TZ transformer. Okay, transformation ratio is nothing but N2 by N1. From that you can calculate the transformation ratio of TZ transformer. Is it clear? Okay, let's move on to the next question. The next question is about, with core type transformers, the limbs are stepped so as to. Okay, so in construction features of a core type transformers, you might have seen the core limbs are going to be stepped form. Why it is stepped form means, like this it will be there. If you see the cross section area of a core, it will be looks like this. The main reason is for this is to make the winding in a circular form. For uniform winding, That means for uniform winding of the core, we need a circular form. That's why the core is going to be like this. That means the core is in the form of stepped. So what are the advantages we are going to get by doing core like this is the length required for the winding. This is winding, this is core. So the length of copper required will be less, required is less. Okay, as the winding is made up of copper, the length of copper wire is going to be less. Okay, if length is reduced, resistance is also going to reduce. Then I square R loss is also going to be reduced. Okay, in order to reduce the some amount of copper losses, we are going to use the stepped core in transformer core. Okay, let's see the different options. Reduce the iron material and therefore iron losses. No, iron losses are not depends on the iron core. Provide better cooling. No, with this we can't provide any cooling. Reduce the conductor material and therefore reduce the I square R losses. Our option is C. We will see the D option also. Provide more mechanical strength to the core. No, it may not provide any strength to the core type of transformer. Okay, so our suitable option is C. In a core type transformer, the limbs are going to be in stepped form to reduce the length of the copper wire. Thereby we are going to reduce the copper losses. Okay, let's move on to the next question. The next question is about, while conducting short circuit test on a transformer, the following side is short circuited. Okay, this is also repeated question. In previous session we already explained. Again one more time we will discuss. Some new students are joined. Okay, see, first of all, short circuit test. What are the objectives of the short circuit test is to find out full load copper losses and the equivalent resistance and percentage voltage regulation also we can find out. Okay, in order to calculate these parameters, we need to conduct the test at rated current. The rated current we may apply at primary side or we may apply at secondary side. That means we may apply at HV side or we may apply at LV side. Now we need to decide which side we need to conduct the test. That means if you see the transformer connection, let's take this is a HV winding and it is a LV winding. So we already discussed the kVA of a transformer is same whether it is a HV winding or LV winding. So in order to make kVA constant, the voltage and current parameters are going to be changed. In LV side, voltage will be less, current will be high. In HV side, voltage will be high, current will be less, in order to make a constant kVA. Okay, so if you conduct a HV short circuit if you short circuit at HV side, for suppose if you short circuit at HV side and we need to energize from the LV side, what will happen? In order to generate rated current in HV side, we need to run the transformer at a very high currents. Okay, very high currents, and the meters required, that means ammeter and voltmeter or watt meters will be high rating meters we required, and whatever the energy is used for testing is going to completely wasted to meet the losses. Okay, so in order to do the testing at efficiency, what we are going to do, we will prefer short circuiting at LV side. What are the different advantages you are getting if you short circuit at LV side? So meters required will be low rating meters required. Second thing is very less voltage if you apply, that means part of rated voltage x into u1, part of rated voltage if you apply to HV side, it will drive the rated current in LV side. Okay, so very less energy is going to be utilized, very less energy we are going to use to conduct the test. Okay, these are the different advantages are there if you short circuit at LV side for short circuit test. So our option will be B. Is it clear? This question already we discussed in the previous session. Since so many new students are joined, so I explained again. Okay, let's move on to the next question. The next question is about a transformer has at full load iron losses given as 900 watts and copper losses of 1600 watts. Then the transformer will have a maximum efficiency at load of. Okay, so we'll write the concept, on which concept the question came. Okay, concept is about efficiency. Okay, concept is about efficiency of transformer. What are the different formulas we remembered related to efficiency? So we need to come to the formula with the given data. What are the given data? One, iron losses are given, copper losses are given, and they are asking efficiency. So we know at maximum efficiency, they are telling about maximum efficiency. Okay, iron losses is equal to the full load copper losses, where x is the fraction of full load, what they are telling at then the transformer will have maximum efficiency at load of, that means they are asking the parameter x. So from this formula we can calculate x is equal to square root of iron losses by copper losses. From the given data, if you see, what is the iron losses? Iron losses is 900, copper losses are 1600. Okay, so 900 divided by 1600. Okay, let's apply the square root. It will be 3 by 4. So it is going to be 0.75. They are asking in percentage. So the percentage x is equal to 75%. Option is C. Okay, is it clear? So whenever problems came, don't get panic. Just note down the given data. Just revise your concept and write down the formulas related to the given data. Okay, you may having many formulas related to the maximum efficiency, but we need to come to the point with the given data. Okay, the related formula should be related to the given data. From that you can calculate very easily. Is it clear? Okay, let's move on to the next question. The next question is given as a transformer possesses a percentage resistance and percentage reactance is 1% and 4% respectively. Its voltage regulation at power factor of 0.8 lagging and 0.8 leading. So the concept is about percentage regulation. Of transformer. What are the different formulas we remember regarding percentage regulation? Percentage regulation is given as percentage R cos pi plus percentage X sin pi. In general it will be plus or minus. So many of the students are going to do mistake here only. Okay, how in order to choose the sign, plus is for lagging power factor, minus is for leading power factor. Okay, the selection of formula will be depends on the given power factor. What they are asking at both, that means at lagging power factor what is the regulation of a transformer, and what leading power factor what is the regulation of a transformer. Okay, let's note down the given data. What is the given data? Given data is percentage R equal to 1%, percentage X equal to 4%, and power factor is given as power factor cos pi is given as 0.8. We need to calculate from here is sin pi also. Sin pi equal to 0.6. How we can calculate? We know that sin square we can find out from this formula also. Since we know we may not having going to use the calculator in examination, we need to remember some basic formula. Sin square pi plus cos square pi is equal to 1. From this formula we can calculate sin pi. Okay, so let's substitute the given data. First we will calculate at lagging power factor. Let's substitute the given data into the formula. Percentage regulation is equal to, what is percentage R? 1, cos pi is 0.8. This is plus, for lagging power factor percentage X is 4 into 0.6. 0.8 plus how much it will come? Let's calculate. Will be 2.4. It is going to be 3.2%. Okay, at leading power factor percentage regulation is equal to 1 into 0.8. we need to take minus for leading power factor 4 into 0.6. it is going to be 0.8 minus 2.4. it will come around minus 1.6 percentage. So our option is B. Our option is B. Okay, is it clear? So this is also a repeated question many times in so many competitive examinations. That means percentage regulation means we need to remember only two things. One is formula, another is that regulation curve of versus power factor. I already explained in the previous sessions. Okay, just we need to where we need to focus is the selection of formula. Okay, so for lagging power factor it will be plus, for leading power factor it will be minus. If you just focus on that, it will be very easy. Okay, let's move on to the next question. The next question is about a 100 volt by 10 volt 50 VA transformer is converted to 100 volt 110 volt auto transformer. The rating of the auto transformer is, okay, the rating of the auto transformer is, what they are telling, the concept is about calculation of, by reading the question we need to identify the concept. The concept is about rating of auto transformer. Rating of auto transformer. I already explained in the previous session and this session also some formulas we need to remember for calculation of rating of auto transformer. What is that? Rating of auto transformer. S auto equal to 1 by 1 minus K into S 2 winding transformer, where S is the rating. Okay. And what is the K? K is the percentage tapping. What is the formula for this? LV divided by HV. So let's note down the given data. Let's note down the given data. What is given data? KVA of 2 winding transformer is given as 50 VA, and transformation ratio, that means V1 by V2 is given as 100 volt by 110 volt. So for calculation of K of auto that percentage tapping, low voltage is 100, high voltage is 110. From this what you can get? 10 by 11. Okay, let's take it as equation 1. Let's substitute the K value in equation 1. What we will get? The rating of auto transformer is equal to 1 by 1 minus K. K is 10 by 11. Okay, what is the rating of 2 winding transformer given? 50. So 11 divided by 1 into 50. So therefore the rating of auto transformer is 550 VA. Okay, the suitable option is D. Okay, is it clear? So from this question what we need to understand is, if you remember the basic formula of auto transformer rating, that means S auto equal to 1 by 1 minus K into 2 winding transformer, and we need to know the formula of K, how to calculate K. Then this question is very, very simple. This is also repeated in many competitive exams. So if you are strong at, finally what I mean to say is, if you are strong at your basics, you can solve any type of question in electrical machines. No need to get panicked by seeing the question. Okay, is it clear? Okay, we'll move on to the next question. Okay, I think the most of the previous questions related to transformer is completed now. So we'll wind up the session for today, and tomorrow we'll discuss some more previous questions related to other concepts. Maybe we'll intimate whether it will be DC machines or induction machines. Most probably we'll prefer to solve the DC machines in the tomorrow's class. Okay, what I request from, my sincere request from all of you is, just prepare previous year questions very well. So if you have any doubt, we are here to help you. You can contact our number at any time. Okay, we are providing test series, offline classes, as well as personal guidance also. Okay, so please share the link to your friends so that it will give little encouragement to us to do more sessions on YouTube. Okay, thank you. We'll end up the